This section is network address translation and aids in the conservation of the IPv4 address space. The continued growth of IP networks in general has resulted in an ever-increasing pressure on the IPv4 address space and the need for a way to prolong the depletion until long-term solutions are founded. Network address translation has become well established as the existing solution and widely implemented within enterprise networks. Many variations of NAT have been developed, thus conserving the public address space whilst enabling continued public network communication. This section introduces the concept of NAT along with examples of common NAT methods applied for maintaining internetworking between the enterprise network and the public network domain. So upon completion of this section, it is generally expected that trainees will be able to list some of the different forms of network address translation, explain the general behavior of NAT, as well as configure NAT to suit application requirements. As a result of the continued depletion of the IPv4 address space, an increasing requirement for addressing to support more and more networks, and with no long-term solution immediately available, the short-term solution to implement private and public network boundaries was applied. In effect, this allows the same private addressing range to be applied to multiple networks, which will have no major impact as long as these networks never intersect. This is effectively prevented since the addresses reserved as private addresses can never be carried into the public network domain. It is still required, however, that traffic from one private network be able to reach the end stations located in another private network. In order to achieve this, addresses must be translated at the edge of the private network domain and represented by public addresses. If we follow the example shown, the private network containing the addresses in the 192.168.1.0 private address range must be represented by a public address in order to reach destinations such as those that exist as part of or beyond the public network or internet. In order to support the translation of addresses between the private network domain that generally encompasses the enterprise network and the external public domain, a boundary is created, commonly on the enterprise network gateway device that represents the edge of the enterprise network. These domains for these boundaries are referred to as inside and global, and generally denote whether the addresses are associated with the private network or the public network domain. The general operation performed involves allowing traffic associated with a private address to be translated at this boundary and associated with a public address within the global network boundary. We show an example of data originating from host A that is to be transmitted to a destination of 1.1.1.1 in the public network domain. Where static NAT is implemented, the transmitted packet carries a source IP address of 192.168.1.1 and references the IP destination as 1.1.1.1. Once received by the gateway of RTA, the source address used within the private network is translated to a mapped public global address, which in this case is 200.10.10.5. This address is used to represent the packet from 192.168.1.1 in the public domain. We show an example of data originating from host A that is to be transmitted to a destination of 1.1.1.1 in the public network domain. Where static NAT is implemented, the transmitted packet carries a source IP address of 192.168.1.1 and references the IP destination as 1.1.1.1. Once received by the gateway of RTA, the source address used within the private network is translated to a mapped public global address, which in this case is 200.10.10.5. This address is used to represent the packet from 192.168.1.1 in the public domain. When packets are returned to the receiver, they are sent to the public address of the sender, which to 1.1.1.1 is the destination of 200.10.10.5. The gateway that performs the address translation is capable of translating the received data back to the private address of host A as a result of the one-to-one mapping that now exists within RTA. Since this mapping is manually defined and therefore fixed, there is no additional burden placed on the gateway device that performs the address translation to dynamically manage the session flows. Where internal networks contain a much broader range of end stations with a requirement for address translation, static NAT is not so practical. We are also able to support a larger number of end stations through dynamic NAT that implements a public address pool to support the allocation of public addresses to end stations located within the private network domain. Rather than assign a one-to-one association of private to public IP addressing, Dynamic NAT uses the pool of public addresses to operate as a shared resource, in which internal users will be allocated an address from this resource pool and will be as such dynamically mapped to a unique public address for a given period of use. Once the public address is no longer utilized as a resource by the internal host, the mapping will be terminated and the public address returned to the resource pool for use by another end station within the private network. We demonstrate here how hosts A and B wishing to transmit packets to the destination of 1.1.1.1 will be allocated unique public addresses from the address pool assigned on the NAT router, which in this case includes just two public addresses of 200.10.10.11 and 200.10.10.12 in the 200.10.10.0/24 network range. The use of the dynamic addressing means that a pool of addresses sufficient enough to support the number of end stations communicating beyond the current enterprise is needed. As the number of hosts increase, so must the relative number of supported public addresses available in the address pool. While Dynamic NAT itself is likely to utilize a large number of pool resources in order to support an equally large number of internal end stations requiring public addressing, an additional mechanism in the form of network address port translation can be implemented, and generally is implemented by default in VRP to greatly minimize the number of public addresses that are needed to support the internal users. We find that the same principles of Dynamic NAT apply here, with the same pool of addresses being used that currently lists two addresses. The major difference, however, is that instead of associating each internal host with a unique public address from the address group, two users can be assigned the same address. The distinction is made based on the port address mapping that is used to uniquely map to the relevant host internally, even where the same public IP address is used for multiple hosts. Traffic intended for internal hosts using the same address are still forwarded to RTA, to which RTA will perform translation based on both the IP address and associated port number. Another form of address translation that relies on mapping through port numbers is what is known as Easy IP. This again can be understood as a form of dynamic address mapping. However, where Easy IP is implemented, there is no requirement for an address pool from which to assign addresses. Instead, the outbound interface address, which in this instance is 200.10.10.1 of interface serial 1/0/0 is used as the translated address. In respect to the example shown, each internal host will be allocated a public address of 200.10.10.1. However, for each internal host to be distinguished, a port mapping is also performed to ensure that traffic can be returned to the correct internal destination. If we take 192.168.1.1 for example, we find that traffic is associated with port 1025. On the outbound interface, the interface address is used together with port 2843. Traffic returned and destined for port 2843 of 200.10.10.1 can be simply mapped back to 192.168.1.1 with a port of 1025. A similar process also takes place for host B. The enterprise network may also wish to house servers that are able to support users located in the public domain but exist within a private network. At the same time, we may wish also to protect these servers from security threats, such as denial of service attacks that may result in a lack of availability of services. The private network domain can be understood as a form of natural barrier that defends against external attacks, and this feature is utilized somewhat through the NAT internal server solutions. Internal servers are associated with a unique public address that can be used by external users in the public domain to reach the server. The NAT gateway will in fact receive all traffic destined for the server and can again perform the relevant mapping to the internal address. What's more is that the NAT internal server solution may be used to also translate the port number from an external port to an internal port that helps to prevent users searching for open ports to attack in a process known as snooping. Any attempted attacks to an address and associated port number will result in attacks to only the NAT gateway that is expected to be able to take action against such attacks and protect the internal server. We show here how translation from network address 200.10.10.5 port 80 to address 192.168.1.1 port 8080 is performed. External users will not be able to discover the true address or port number of the internal server. Now that we have observed the more common forms of NAT and familiarized with their operations, we can go ahead and look at some of the commands used to implement them within the NAT gateway. We must firstly ensure that we have network layer connectivity between the gateway and the external network, as well as between the gateway and the internal host or end stations. Host A in this instance can be understood to be part of the same network as interface gigabit Ethernet 0/0/1, which has the address of 192.168.1.254. The public address of 200.10.10.1 is used for interface serial 1/0/0. For host A, however, we use the address 200.10.10.5, and we see this configured as part of the NAT static command, in which a global and inside mapping of the address is performed, in order to allow host A to be recognized as having the address 200.10.10.5 in the public domain. If we use the command display NAT static, we are able to identify which static mapping entries between private addresses for internal end stations and public addresses exist. In this case, we have only configured a single static mapping, which can be clarified by the total at the bottom of the display output. We can determine that this mapping has been applied to interface serial 1/0/0, in which the internal address of 192.168.1.1 has been mapped to the public address of 200.10.10.5. For the configuration of dynamic NAT, we must perform a number of tasks. The first of these is to define an address group that will be used as the pool of public addresses that can be assigned to internal users. Typically, the public address range will be assigned to an enterprise by the service provider, and so the address range that is assignable depends on the number allocated to the enterprise. Here we demonstrate having a public address range known as an address group from 200.10.10.11 through to 200.10.10.16 that is used within the NAT address pool. A set of rules are also created that tells the NAT router which internal host addresses can be translated. This set of rules is known as an access control list and will be introduced in more detail later. The access control list, however, is associated with a number, which in this case is 2000, and is used to reference the rules that will be applied to the dynamic NAT. Finally, the command NAT outbound is used, to which we reference that for users in the 192.168.1.0/24 range, these users should be assigned an address from the pool associated with address group 1. We have also included the parameter NOPAT that will prevent port address translation from being performed. If we wish to implement network address port translation, the NOPAT parameter should be excluded from the command. For the dynamic NAT configuration, there are two commands that can be used to validate the configuration. The first is the display NAT address group command that is used to determine the range of addresses that have been assigned as part of the public address group. In this instance, we can see that a range from 200.10.10.11 through to 200.10.10.16 has been assigned. We are then able to use the command display NAT outbound in order to verify whether the dynamic NAT configuration has taken effect on the interface. This includes the binding of the NAT configuration to the correct ACL number that represents the private address range to be translated, and the address group, which references the range of public addresses to be used. We also see here that the type is listed as NOPAT, meaning that port address translation will not take place, and that internal hosts will be allocated public addresses exclusively. With EasyIP, we find that configuration is similar to that of dynamic NAT. However, there is no requirement for an address group to be defined, as the outbound interface address will be used as the public address for the internal host. We still, however, are required to identify the internal address range that is to be translated using EasyIP by the NAT router, which again is shown here to be the network address range of 192.168.1.0/24. Under the interface view of the outbound interface that contains the public IP address that is to be translated, we apply once again the NAT outbound command. However, only need to specify the access control list that identifies the internal host to which translation is to apply. We again have no requirement to specify an address group. We can again use the display NAT outbound command to determine whether the EasyIP configuration has taken effect. From this output, we are able to determine the outbound interface to which translation is associated, the outbound IP address that is used, and the type of NAT that has been applied in this instance, which of course is EasyIP. If we are implementing internal servers that are to support external users, we are able to configure the following commands to allow the server to operate as part of the external domain from within the private network. We show here that the internal server currently is associated with IP address 192.168.1.1 internally, and from the configuration, we should understand this to be a web server that is associated with the IP address 200.10.10.5 in the public network domain. The command NAT server references that only packets containing TCP headers should be accepted, with a destination of 200.10.10.5 and a port number of 80. The www here is equivalent to the well-known HTTP port, or port 80. For such packets, they should be translated to the inside destination IP address of 192.168.1.1 and use a port number of 8080. The server itself should also be listening on port 8080 in order to receive the TCP-based web traffic. We can use the command display NAT server to confirm the configuration has successfully been implemented on the router. In respect of this, we find that the NAT server configuration has been associated with the outbound interface of serial 1/0/0. Traffic being received externally and destined for the public address of 200.10.10.5 with a port number of 80, we find will be translated to the internal private address of 192.168.1.1 with a port number of 8080. We see also here that this translation is only associated with TCP packets, which in the protocol field of the IP header represents a value of 6. So we come to the summary for this section on network address translation, and we have just a couple of questions here. The first is, which form of translation will allow a server in a DMZ to be accessed from both an external and an internal network? Well, we are able to use the NAT internal server configuration to support network address translation for servers located within the DMZ, so as to prevent traffic flow originating externally from entering the private and what we can understand to be the trusted area of the enterprise network. And what is the function of the PAT feature? Well, through the PAT feature, we're able to perform translation based on the port number in addition to the IP address. The port address range allows for a single IP address to support a large number of internal users, and therefore provide an effective means of public address conservation.